So what is dynamic programming? We talked about greedy algorithms in the last class. Dynamic programming, divide and conquer, greedy algorithms, very similar. What's the difference between divide and conquer and dynamic programming? Quickly? Overlap is one word answer. In all three situations, greedy, dynamic, and divide and conquer, we are solving big problems using solutions to sub-problems. Dynamic programming and sub-problems are independent. Divide and conquer, when sub-problems are independent, we use divide and conquer. When sub-problems overlap, we use dynamic programming. In some situations, in every stage in dynamic programming, you have multiple sub-problems to solve. But if you go down one path, you still get the optimal solution. That depends on the nature of the problem. And if your problem has that property, then we can solve it using greedy algorithm. We can make a greedy choice rather than taking care of all the choices. So in a nutshell, that's what it is. We'll look at two big problems today. So dynamic programming is another strategy for designing algorithm. It's not an algorithm. It's a technique, a meta technique for designing algorithm. And then when problems break down into recurring small sub-problems, that's when we do dynamic programming. Again, simple sub-problems, optimal substructure of the problems. That's also very important. So you take a look at a problem. So you take a problem and you break it down into sub-problems. If the sub-problems do not have optimal substructure, by the way, what does quickly optimal substructure mean?
Solution to the substructure will be the same.
Wait, one by one. One step, yeah.
The solution to the sub-problem will be in the solution to the initial problem?
Yes. To solve the bigger problem, you must be able to use the solution of the sub-problem. So the sub-problem solution gives you solution to the bigger problem. So you take a problem, it's some problem, and you design the sub-problems for it. And you see that the optimal substructure is not there. That the solution to the sub-problem is not useful for the bigger problem. Does that mean you cannot use dynamic programming for it? No. Did I not? So you take a problem S, and you divide it into sub-problems, say S1, S2, Sn, right? And now, these sub-problems may overlap. Maybe the solution to S is the solution to Sn, which is the last sub-problem. These sub-problems overlap, but what you see is that solving S1 doesn't help in getting a solution for S2. Or solving S1 doesn't help in getting solution for some S5. My question is, would you say this problem does not have the optimal substructure property?
No.
No, why?
There might be a case where we are not dividing it in a way that it helps.
Good, yes. So you take a problem, you break it down into sub-problems, you don't see optimal substructure property. That does not prove that this problem does not have optimal substructure property. Maybe the way you are defining your sub-problems doesn't give optimal substructure property. You have to define it in a different way. And try to figure out sub-problems in a different way, and then you might get optimal substructure property. And we'll see one example today of that. But keep in mind that it's the way you find the solution or the algorithm that you are coming up with that should give you the optimal substructure property of the problem. If you're coming up with an algorithm that breaks down the subproblem in such a way that the substructure property doesn't help, then you're not going the right way. Right? You will not be able to solve it using dynamic programming. Okay, subproblem overlap, like we discussed. Problems overlap, then we can use dynamic programming. We'll look at the LCS problem, the first problem. Let me explain to you what the problem is. Let's just use this sequence. So say we have the sequence A, B, read the sequence to me, C, D, and B. A, B, C, D, B. Let's just use 5, and then we have B, D, C, and A, B. So the longest common subsequence problem, the LCS problem, is basically to find, given two strings of characters or given two sequence of characters, the problem is to find the longest common subsequence. This problem has a lot of applications. In bioinformatics, there's a lot of applications to LCS problem and so on. So what is the subsequence? We defined that last time. What's the subsequence?
They occur in the same order.
of the subsequence.
Basically, B, C, B. Is that a subsequence of this sequence?
Yes.
Yes, it is yes. It's not a substring, but it is a subsequence. So how many subsequences can you have for a string? We discussed this last time.
And
So 2 raised to the power n is the number of subsequences. Basically, you either include this character or you don't include this character. You include this character, don't include this character, and so on. So if you have n characters, the decision is 2 for each one of them, and 2 times 2 times 2 up to the power, basically multiplied with n times, you get 2 to the power n. So, what could be a naive algorithm to find the longest common subsequence in this? You don't care about the complexity. Just give me one that works.
All possible combinations and then try to.
Tell me, well, what could that be? So in this case, you got 2 to the power 5, which is equal to 32 subsequences of this string. And you got 2 to the power 5 equals 32 subsequence of this string.
then you compare.
So what?
Comparisons, 32 factorial comparison.
So you compare what with what?
All the subsequences. So you compare 32 plus 31 plus 30 plus 29, like that many comparisons. Like sum to 32
So you're saying compare each subsequence here
to each
with each subsequence here.
You can just find that.
Or you can compare the subsequences of same length to
You compare subsequence of same length also, but you can even reduce it by, if I ask you, is ABD a subsequence of this? How would you go about finding it? I'm not asking you the longest common subsequence. Given a subsequence, you want to check if that is a subsequence of this string or not. Match the first character, you got it. Match the second, after this. Look for the second character. Doesn't have to be contiguous. You got B, and then string ends. D is not a subsequence. If I do B, C, B, you basically match first. You got the first one, now C, get another C, you got the second one. Now you look for B, you got B, you got the third one, and C. So in linear time, you can compare, given a sequence, whether something is a subsequence of it or not. So you do not need to compare every subsequence with every subsequence. You can take these 32, don't take these 32, just check. Start with the largest length, check if that is a subsequence of this or not. You see what I'm saying? List out all and check. So you got 2 to the power n, and each checking involves n. So you got an n 2 to the power n algorithm. Right? That's your brute force, naive algorithm to solve the longest common subsequence problem. But obviously that's not acceptable. Why? Exponential complexity, too much time it takes, and so we will come up with a different dynamic programming approach. Now before that, let's quickly check, is there an optimal substructure property? So if I give you the subsequence of this and this, will that help in finding the subsequence for the whole string? Yes, it will. And so it seems like it has optimal substructure property. Now we're going to come up with a recursive solution, as we do in dynamic programming, to solve the longest common subsequence problem for these two sequences. How do we do it? Now what I want you to find is not the longest common subsequence. Let's make it easier to begin with. We'll try to find the length of the longest common subsequence. I'm not interested in the longest common subsequence at this point. I'm only interested in the length of the longest common subsequence of these two strings. What's the answer, by the way?
5.
What?
No, 5 is
I mean, individually, the longest subsequence
It's
will be
BC.
the C. I mean, be the whole.
Length is 3.
What is the length of the longest common subsequence? 5.
3.
Okay. Which one is it? B, C, D. B, C, B. Right? Or B, D, B. Yes. Let's go with B, C, B. So I'm not interested in finding this. I'm only interested in finding the length of the longest common subsequence is 3. How do we do it? So, again, in recursion, to find the length of the longest common subsequence for these two, I'll let you ask me a question. What would that question be? See, again, do remember, we are only interested in the length of the longest common subsequence. So my question to you is, what's the length of the longest common subsequence for these two? Right? But rather than answering that, you need to ask me a question, and then with my response, you figure out the length of the longest common subsequence. What your question would be. If you're allowed to ask, say, 3 questions. I mentioned this in the last class also. So say this whole thing is X, this whole thing is Y. What I want you to find is, say, L of X, comma Y. That's what I want you to find. What will you ask me? So let's name them.
Can we apply?
So let's call it this one lowercase x and lowercase y. Okay, which I'm leaving this. So if I give you the length of the longest common subsequence of L, basically length of longest common subsequence of x and y, the lowercase x and y, would that help? Okay, so I tell you the length of the longest common subsequence is BC, BC. Do you have anything else? Yeah, length is 2. So then how does it work? Add plus 1, okay. So you are saying this is equal to the length of lowercase x comma y plus 1. If the last characters are the same. Okay. We're going to write it formally, last car same. What if it is not same? Say just for, so the last character is not same. Say this is A. Then it's 2. Then it's 2.
No, it's LX, small x y. I mean, it will be the same.
So think about it. You guys are saying then this will have no impact on that, right? Let me see. Okay, so let's see. Again, guys, pay attention now. No talking. Let me change this to, so what is, forget about this last character. What is the longest common subsequent in the lowercase x and lowercase y? What's the length? It's BC, right? BC or BD, right? BC or BD. Okay? Now, you are saying as long as this is different. If they are different, then you will not have any impact.
We will have.
Basically, if this is 2, this is 2, the answer will be 2. Now see,
No.
the magic. If I make this D here, B and D are different. So now tell, so forget about this. Forget about this. What's the length of the longest common subsequence here? We agree it's 2. If I add the same character, it becomes 3. Easy to understand. But if I add different characters,
It might
Will
be
it
2,
always
might
be 2?
No.
No.
Okay, good. So that you are saying, if I add B here and I add D here, because this will give you BCD, this gives you BCD. You see that? So adding this D here, the whole thing now became 3. So how do you write that rule? So the rule where the last cat is same is this. Where last cat not same, what is the rule?
Checking small x with big y.
Shift X to space and
Exactly. So now what you need to do is, you're going to ask me the question. See, the only thing you cannot ask is what is Lx comma y. But you can ask everything else. So you'll ask me, what is L of x with uppercase Y? And you will ask me, what is L of uppercase x with lowercase y? So that is asking, what's the longest common, length of longest common subsequence of this with this whole thing? That's different from this. So you're allowed to ask. And then you're asking, what's the longest common subsequence of the whole thing with just this part? Right? It'll make sense. So, what's the longest common subsequence of this part with this whole thing?
2.
What? So, the answer is, so in this case, what's the answer? You got B, C, that's it, and then you got B, C, right? So this is 2, but if you take, so this is,
Big X, little y.
this is, what does this give you? The lowercase x and big Y gives you 3, and this gives you 2, right? And so, when the last characters are not same, then you take the max of these two values. Does it make sense?
Yeah.
See, again, this problem in dynamic programming, at least to me, and I'm sure to many of you, at the outset it seems really hard. But once you try to understand this recursion and try to solve it recursively, it seems very easy. So so let's write it formally. Let's write the same thing that I've explained here. So what?
Professor, what will be the base case of the?
Yeah, I'm going to tell you the base case. Without the base case, this won't work. You know that, right? Without the base case, this won't work. So what would be the base case?
Last character is the same.
So the last character being same or last character being not same, if you see to compute LXY, I am using L. The base case is when you have L something comma something is equal to a fixed number.
1.
Gravity is 0.
So that's why I wanted to formally define it, and then it will become easier to see the base case. Okay? So let's define it this way. Everybody with me? C is going to be, say just call it C instead of L. It's different. C of I comma J. C of I comma J is the length of the longest common subsequence by taking the first I characters from the first sequence and taking the first J characters from the second sequence. Does that make sense? So Cij is the length of the longest common subsequence if you consider the first I characters of the first sequence and the first J characters of the second sequence. You got two sequences, I and J. And do see that they don't have to be of same length for you to compute. And we'll see that once I start drawing the table. We'll see that. So this is how Cij is defined. So what would be the rule? The two rules according to that. So Cij is equal to C I minus 1, j minus 1 plus 1, where say the sequences are A and B, right? A sub I is equal to B sub j. Okay? Let me remove all these X and Y now that you guys understand. And what's the next rule? It is max of C I minus 1 j comma C I j minus 1 otherwise, right? Where this is not equal to this. So you can say where A sub I is not equal to B sub j. Does that make sense? So this is your recursive rule.
So essentially the path problem itself, no? The path problem that we did previously, it's the same thing only.
That's right. Very similar to that. Yes. That is correct. So what's the base case? The base case, if you look at, yes.
So if A1 is equal to A1 and B1 are the same, then the base case is 1, else it's 0.
No, what is the base case? See, the base case is, if you write C,
yeah, C11 is equal to the 0 or 1.
If you write C11, think about it. So base case should be something that you should not be able to apply this rule to. Can you find the solution, or can you find the value for C11 using this? Yes, you can. Right? See, what's the base case for factorial?
0.
0 factorial. Can you find the 0 factorial by this rule? Fn is equal to n times f of n minus 1. When f is the factorial. Right? You cannot. So the recursive rule does not apply to the base case rule. Remember that example of the guy asking the person in front, what's his row number? We keep doing it. The person sitting in the very first row, he doesn't have the luxury of asking the person in front. So that recursive rule does not apply to base case. Should not apply to base case. If it is applying, that means you have not chosen the right base case. So what value of C, comma this, should we have for which this will not work? So look, we need I minus 1 and j minus 1.
I minus 1 should be greater than
Oh,
C11 should be equal to
C10 and C01.
What is C00 by the way?
The first two characters.
C0 is not the index.
Yeah, it doesn't
See,
exist.
I is not the index. Don't confuse with that. I said Cij is where I take the first I character from the first sequence. So if I put 0 there, it is the first
0 there.
So I
first 0 character. So if I take no characters from the first sequence and I take no characters from the second sequence, what's the maximum, what's the length of the maximum or the longest common subsequence? 0. There's no question there.
Undefined.
What if it's not undefined? Undefined has a very different meaning. Don't use undefined for 0. Right? So, undefined is something that cannot be defined. Very simple. Can't just be defined. If you got nothing from here, what you got? Nothing. Nothing means 0. Doesn't mean undefined, right? So, now, what if you take 0 characters from the first subsequence and take 1 character from the second subsequence? Still 0. What if you take, so if I just give you that C of 0, 0 is equal to 0. That's the base case. This we cannot figure out from here. Is there any other Cij value that we cannot figure out from here?
2 more.
Wait, raise your hand. So my question is, see, I'll have to go from C00 all the way up to C55, right? And C55 is my final answer, right? My question is, this rule will give me most of the values. Is there any other Cij that I cannot figure out by these rules? Can I figure out C1, 0 from this rule?
No.
Can I? No. Because I would need to do -1 for both I and j. Can I figure out C0, 5 from this?
No. So we have 3 conditions for a base case.
We have many conditions for base case, not 3. But you're right, it can be written as 3.
But you will never reach 2, 0 and 3, 0, you'll never reach that condition, right? Because it's always I and j -1 or j
Exactly.
I -1.
So all the zeros for any value of I, so basically all the values where you got C(I0) is 0 and C(0j) is 0. For all I, j. Does that make sense? And why is it 0? Not just because I'm putting a 0 there. What does it mean? So if I have 5 characters from the first subsequence and 0 from the second, what's my longest common subsequence? It's length 0, right? And so logically, these are the base cases. Once you have this, then you can solve this. Now let me quickly draw the table. So say if this question is asked, how would you go about doing it? Any questions? Okay. So given 2 sequences like this, guys, don't talk because it's too loud. Now, given these 2 sequences, how do you go about finding the longest common subsequence? We're going to use this rule. So given 2 sequences, what the first thing you do is you draw a table where you will have, for example, the sequence, you write the first sequence, whichever way you want, C, D, B, and you write B, D, C, A, D. This table that I'm drawing, I don't have it on the slides. It's in the book. And so if you're taking notes, definitely take notes. Otherwise, like I said, it's in the book in great detail. So say these are my 2 sequences. Let me call it, so this is my X, this is my X, and this is my Y. Right? Now, sorry, I just realized that we need to have a choice of not taking any character. So let's just write A, B, C, D, B here. And this would be the row where I'm not taking any character. So this is B, D, C, A, D. So what are the I and J values? So I values here will be 0. This is 1, this is 2, 3, 4, and 5. And the J values will be here will be 0, 1, 2, 3, 4, and 5. Guys, so, and this table represents the C of the values that you're going to put there is the length of the longest common subsequence of Cij. So when I is 0, whatever may be j, what's the value you get? 0, 0, 0, 0, 0, 0. What else can you decide?
Whatever j is 0.
When j is 0, so this is I and this is j. So when j is 0, whatever I may be, you got 0, 0, 0, 0. See how fast it was? Simple. Now what do you do?
Now you compare if there's a same number, you add 1. If they're not,
Now, sure. So
you choose
now
the
we
maximum
apply
of top and left.
these rules. How do we go about filling this table? You can go in whichever way starting from this point. You can fill this row, then you can fill this row if you want, and so on. You can fill this column, column if you want, and so it's fine. As long as you have these three values, you can fill this. Why? Because this represents Ci minus 1 j minus 1, this represents Ci minus 1 j, and this represents Ci j minus 1. Right? So to be able to compute Cij, you just need either this or this and this. That's all. So let's quickly do what's the value here. Now wait, don't blurt out the answer. What's the value here? You will have to figure out whether to apply this rule or this rule. Which rule applies in this case? The second one. Why? Because A and B are unequal. So x of 1 and y of 1. So I'm trying to find C of 1 comma 1. That's what this value is, right? That's what I'm trying to find. C of 1 comma 1, for that I need x of 1 and y of 1. If they are equal, then this rule applies. If they're not equal, then this rule applies. So in this case, x of 1 is x of 1 is A, and y of 1 is B. They're not equal, so the second rule applies. What does the second rule say? Find this, and write the maximum of the two. So I got the value 0 here and 0 here. I write the maximum of the two, which is 0. Okay? At this point, I also have the luxury of knowing which value made an impact. So for example, if this was 1, what would this value be? 1. So it is actually this value that you got. Right? If say this was 1, then you're copying this value. If say these two were equal, then this value will make the impact. So whichever number you are using to make the decision for this is the one you will call the parent of that number. This parent information will help later on to compute the longest common subsequence. So if this is 0, which one would you take? This one or this one? Which one is the max? They're both equal, doesn't matter, whichever one you want to choose. So I'll just put an arrow here, just for now. Now what about this one?
Same thing.
Same thing. You got 0, now you can put an arrow here, doesn't matter. This one, same thing, 0. This one,
1.
you got 1.
But impact didn't come from anywhere. It came from the.
So what?
Impact came from the clause we have there.
Right. So this will be 1, but it will be because it's equal. Right? What about this one?
0. Oh, it's 1. Taking from the previous one, it's 1.
Second condition.
So once you get to this, now what I'm trying to figure out is you get to this and then you can go back, we'll have to figure it out. So this is also 1, but it comes from here, right?
Yep.
Right, okay. Now, actually once you reach this, you have reached the longest
For the first.
common subsequence. Okay, so do you see how you can fill the whole table up? Let's quickly do it. What's the number here? 0? Is it 1? Because you have B and B. Sorry, 1. And then what's the number? 1 here, B and B. And the number is coming from here. This is also 1.
1 again. 1 again. 1 again.
You got 1 again?
Yeah.
You got D and B. And so you can take it from here or here. Both of them are 1, so this will be 1. What about this row? C and B. You got 1, and it's coming from here. Right?
Right.
And then you got C and D. 1 coming from here. Matter. Then you got 2 because C and C. That's coming from here. You got 2. And then what's the number here? 2 here. 2 here. Now let's see. This is 1 coming from here. You got D and D. You got 2 from here. Then you got 2, 2, and you got 3.
Yeah.
Okay,
Here,
and then
2.
you got 1
2
here.
because it's common.
No, 2 from the.
No, because you're
No, it's coming from there.
4, 0.
So it's 2 now.
You add 1.
See, when B and D are equal, these two don't matter. It's actually this. You're getting from. You got 1 here, and then you got B and D. So you got 2 coming from here. You got 2 still coming from here. You got 2 coming from here. And this is got 3 coming from where? Right? And now let's see. So this is easy to fill the table. Let's see if we can figure out the longest common subsequence from this. So we know, well, what's the solution to this problem, by the way? So you got Cij, and you wrote this rule. This is of length m, and this is of length n. Then what's the length of the longest common subsequence for this? It will be given by C, m comma n.
Yes.
So it's this last number that you have here. That's your solution. That's the length of the longest common subsequence for that problem. Now, how can we recreate? What is the sequence? You start from here, you go here. Now, if you are going up, you don't include that. But the moment you go this way, now you include that character, right? And so, see, whenever you go here, these two characters will be the same. So D is the last one. You see? And then you take 2, 2, 2, and now you go up here. C is the second last one. You basically follow this, you get the longest common subsequence in the reverse order, right? And then you go here, and where do you go? Here and here, you got D as, so you got B, C, D. But there is another sequence here, right? So B, C, D, everybody understands how I got it? Sure. So you're going to start from here, and you're going to go to the parent. When you go to the parent, if you are taking this straight, the horizontal or the vertical arrow, then you just keep moving. Whenever you go diagonally, that's when you get the character. It'll have the common character. So I go from here to here, nothing. It doesn't. It's just guiding me. But now from here, where do I go? I'm going diagonal. So when I do that, you will see what happens is the character here and the character here is the same. That's why we go diagonal, right? So that you're going to keep. So you put D. Now, then you move here. Now from here you're going horizontal. Doesn't matter. Now here you go diagonal up. So this is the character that you're going to take. So you got C. Okay, you collected D and now you collected C, and where are you? You are here. And now you move left, and then again you go diagonally up. So the character that you have is B. So wherever you move diagonally up is where you will collect. So this one and this one. So you look at these 3 circles that I drew. You see the character that you have here and the character that you have here is the same. Then only you move diagonally up. The character that you have here and the character that you have here is the same. So you collect that, and then you move up. The character you have here and here is the same. You got B. Now, DCB is what you collected. Reverse it, and that's your longest common subsequence. So moving from here all the way up to this row or this column or this row is when you stop. Keep going there, and then you stop. Now reverse this. You got B, C, D as your longest common subsequence. Okay? Everybody clear?
So it's the same problem that we saw that time.
Sure. What did you say here?
That's a lot of work.
A lot of work? You don't have to do it. You just need to understand it and program it.
I hope we don't get to solve this in the paper. It will take
Why?
time. It'll be the same thing as that problem we had in the midterm.
The hashing.
Hashing problem.
It doesn't matter. Okay. You may have it, you may not have it. Look at the second problem that I'm going to show you, then you can choose one. Yes.
The idea of
Which one?
the diagonal in first row. That is when I is 1 and j is 5.
So you basically what I'm saying is you start from here. Guys, again, don't talk.
No, not the last part.
This is a class, guys. Come on. Other people are asking questions and they're getting answers from me. If you have a question, ask me. Please. Yes.
The very basics. So when I is 0, sorry, no, I is 1 and j is 4. So you,
I is 1
and j is 4.
and J is 4.
That diagonal, can you just explain that part again?
So this one, see the reason so how do you fill this number here? You got A and you got A, and they are the same, right? A and A are the same. A and A are the same, so which rule will apply?
First one.
First row.
The first one, which says see I minus 1, J minus 1 plus 1. So whatever this number is, you add 1 to it and you put it here, right? So 0 plus 1 gives you 1. And now which number helped you in getting this 1? It's this number, and so you just make an arrow here. This arrow will help you later on in figuring the longest common subsequence. Okay? Now when you have two numbers, so here you got 0 because of this or this. They are the same, doesn't matter, so you can put arrow whichever way you want. That will only guide you to the longest common subsequence. Now how do you get this? You got it this way, and so it's easy. Now I do want to quickly point out that we'll look at the second problem, and then you can choose which one you want on the exam. But the point is, if this question, say this question is asked, you just need to provide this rule, which is pretty basic, standard, easy to memorize. I'm not expecting you to memorize though. Please don't. Understand it. It's easy to reproduce. And you just produce this table. While producing this table, did you see you compare? So put zeros, and quickly compare. Put a 0 based on that, compare, put a 0. How long did we take? Once you understood what the solution to the problem is, it won't take more than 5 minutes to create this table. And once you have the table, you just follow the diagonal ones, and you'll get the common subsequence. So don't make it an issue if it's on the exam. Now
we choose from 2, right?
we'll see.
Can
Wait.
you choose this one?
We'll see. Wait. Now quickly, this one has another longest common subsequence, right? BCD was 1.
No, it doesn't.
Oh, it doesn't?
So you replace the D with D in the end of Y.
Yes.
Right.
Now it does
Okay.
that.
So, but even if say you got 2 longest common subsequence in the strings, do you see that this number only has one parent? It will guide you to one of the 2 common subsequence. Why doesn't it guide you to the second one?
So there isn't a starting where we can take any of the 2.
So depending on these choices that you make, many of the places you have this choice of going horizontal or vertical. Depending on the choices you make, depending on how you fill this table up, you may get to one of the multiple longest common subsequence. But it will guarantee you that it will give you one longest common subsequence. It's not going to give you all, but any one depending on the choices you make. Okay.
So it's greedy.
So what?
So it's greedy.
It's greedy? No. It's not greedy. So the 3, say if this has 2 longest common subsequence, both of them are of equal length. Any one of them is a good answer. You see what I'm saying? Greedy is when you make choices while coming up to the solution. But what I'm showing here is that two sequences may have multiple longest common subsequence, but they all will have the same length. This will give you one of those multiple ones. Okay? Now let me quickly wrap this up. So again, I'm not going to go into the details. I've shown you everything here. This is showing that the naive brute force approach, it's n to the power n complexity. And then this is the formulation. We have explained this already. Now, basically this is in words, it's showing how the trivial cases should have all zeros. And then the recursive formula for Cij is this, that we have already explained. And so Cmn is the final solution. Okay? After we fill the array C, we can use this data to find the characters that constitute the longest common subsequence, like I showed you. And the algorithm, what is the complexity of the algorithm? Who can tell? So what? M what?
X times
Y.
The length of this times length of this. How can you prove that?
You only make, you go to one of these.
This basically we need to fill these many numbers. How many numbers we got here? Order m times n. And every number, filling every number just requires one basic operation. Or maybe two basic operations, doesn't matter. But it gives you m times n, oops, compared to O n to the power m or n. Right? And so this is so much better. Now we look at another problem. The knapsack problem. So let me quickly introduce the problem and then we'll write the recursive thing. And I'll show you the table and so on. Okay, let's do the knapsack problem. Okay, and so in the knapsack problem, the real world example that's given is, say there is a thief, he's got a big knapsack, but there is a certain weight that that knapsack can hold, otherwise it will tear, and so he goes to some place, and he sees tons of items. He's a pretty smart thief. Looking at an item, he can figure out how valuable that item is, and his decision is to choose from those n items, choose say maybe some m items, m is less than n, less than equal to n, such that he doesn't tear his knapsack and he gets the maximum value. How do you make that decision? So there are two versions of this problem. The first version, those items are, say, a bag of some fine dust, say gold dust or whatever, platinum dust, I don't know what metals have dust. So the bags of these different dusts that are there. What's the difference? If you, at the end, if he wants to fill up, the knapsack has little space, he can open up the bag of dust and fill up whatever quantity that he has space for, right? Versus the second version of the problem is where, say, he has paintings, large paintings or something, things that cannot be broken down. He can choose it to either take that thing or not take that thing, but he cannot break down the two things. So the second version of the problem is called a 0-1 knapsack problem because you have to make the decision of taking it or not taking it, 0 or 1. 0-1 knapsack is solved by dynamic programming. The previous one, that's called a fractional knapsack problem. It can be solved by a greedy method. So let's quickly look at what these two versions are. So every item you have, so say there are a bunch of items, let's call it P1, so we have say P1, P2, P3, say Pn. Each item has a value, V1, V2, Vn, and each item has a weight, W1, W2, Wn. Right? You got the value, you got the weight. So which item do you think, in a naive approach, which item should you choose first? The one that is the heaviest, or the one that is the lightest, or the one that is the most valuable? Is it most valuable or it's most valuable per unit of weight? Per unit of weight. Why? Because you may have, say, the total weight that the knapsack can take is, say, 20 pounds. Right? And you have this item that is worth, I'll have to create. So, see, that is worth, say, $20, but uses up 20 pounds. But then you have another item whose worth is 25. Let's make it less. Got $18, but uses up only 10 pounds. Right? And you got another one that's $15 and uses up 7 pounds. So if you choose the most valuable item, then your 20 pounds that the weight limit is gone. But if you make the choice of taking these two, you got more value. and you still have room for 3 more pounds. Does that make sense? And so the highest value per weight unit is what you want to choose. So you calculate the VI divided by WI for each one, and based on that, you make a decision. So VI, you got V1 divided by W1, V2 divided by W2, and so on. Vn divided by W1. So this helps you. So V by W. If you do the fractional knapsack problem, then what you do is you find these values, sort them, and start putting in the item with the highest value per unit of weight, as long as you can fit it. Now you come to the item that you cannot fit completely, you break it down and fit as much as you can. In the fractional knapsack, you always reach the limit of your knapsack. You fill it up to the brim, right? Or the brim of your limit. So that's a greedy algorithm. The algorithm is find this, sort them, fill it up based on this, and in the end you might have to take a fraction of the last item that you can fit. And everything else you leave because they have very less value per unit of weight. Make sense, everybody? Now let's come to the 0-1 knapsack problem. How do you solve that? So what?
Dynamic programming?
Same what we did with.
Yes, dynamic programming.
Let's ask.
But first, we have to formulate the problem. Wow, time is running. How would you formulate the problem? So I have n items, right? My problem is, so I got a maximum weight also, whatever this W is. So I need to make a choice of choosing these items. So I need to consider all n items. Whatever I choose should give me the maximum value, considering that I don't go overboard with my weight. That's the problem. How do we make sub-problems out of it? So say S is a sub-problem. S of n is the solution to the 0-1 knapsack problem after considering n items. So let's call it I. S of I is the sub-problem, basically solution after considering I items. So what's my final solution when I've considered all the items, Sn? That's my final solution. Say what I do is I take these items, I decide, I make a decision on the first item. Should I put it, should I not put it? Then I make a decision on the second item. So far I've solved S1 and then I've solved S2. What is S2? S2 is not considering the second item. S2 is considering 1 and 2. S3 is considering 1, 2 and 3. S4 is considering 1, 2, 3 and 4. That seems like a good sub-problem formulation, right? My question is, if I give you a solution to Si, does it help you in solving Si plus 1? Let's see. Let's see. You got n items. I am asking you, solve the knapsack problem for n items. You get to ask me a question. What question would you ask? What's the solution for n minus 1 items? Right? You keep the last item yourself. What's the solution for n minus 1 item? And I tell you the solution for n minus 1 item. Would it help you in formulating the solution for the last item? It won't. It won't. And let me quickly show you that. It'll save some time. So I'm going to skip a few slides. These I've already explained. 0-1 knapsack problem. Problem is how to pack the knapsack to achieve maximum total value of packed items. You got the weight, you got the benefit value. Weight and value, 2 are ways. And the problem is to maximize the value, making sure the weight doesn't go overboard. Weight, the total weight that you have selected is less than equal to the weight allowed. Okay, so this part is good. It talks about fractional knapsack that I've already explained. Let's first solve the problem with straightforward algorithm. What could be the brute force naive approach for this? And what's how many combinations? If you have n items, how many combinations can you have?
N squared.
Not n squared. 2 to the power n again. Because you have a choice of keeping the item or not taking the item. So for every item you have the choice, you have 2 to the power n different ways of stealing the items. Right? Which one has the maximum value? You just calculate all 2 to the power n values, see which one has the maximum, done. So it's 2 to the power n. Again, not too good. So we do it using the subproblem or the dynamic program. So items are labeled 1 to n, then the subproblem would be to find an optimal solution for items labeled 1 to k. Will it help? Let's see. So if I have this definition, this valid subproblem definition, question is, if we describe it the final solution Sn in terms of Sk. Unfortunately not. How? Let's look at this. So look at this subproblem. What's the solution for S4? The S4 solution is, if you look at this, 4 things. Actually, this is messed up. This is W2 is equal to 4 and V2 is equal to 5. What is the solution? The solution for S4 is choosing 5, 4, 9, actually everything. For S4, because my maximum weight is 20, I can choose all of these, right? And I still have weight equals 14. Right? You guys with me?
Yeah.
So solution for S4 is, considering the first 4 items, my solution is to choose all of these. Now using that, how can you find S5? So S4, I told you choose all items, all 4 items. How can you find S5? What is the solution for S5? The solution for S5 would be?
S4.
Is it S4? So choosing 9 plus 5. See, 9 has the highest value. So you want to choose that 9, 5, 4, 18, and 2 maybe, 18, 20. So you're not going to choose this. But how does that help? The solution to S4 did not help at all. You just recalculated everything. So solution for S4 does not help in choosing this. So solution for S4 is not part of solution for S5. And so this formulation of subproblem does not have the optimal substructure property. You cannot use this for dynamic programming. We need to figure out something else. You need to ask me a different question. Right? And let me tell you what that is, because we don't have that much time. So the way you formulate it is, so don't worry about what you have on this slide. I'm going to tell you. The subproblem you will formulate is this. You have, say, B is the benefit that you get by considering k items so far. And W as the weight. W is the weight of considering these k items and finding the optimal solution. So, if I choose 3 items out of 5 items, then this W represents my weight, exact weight of those 3 items. Does that make sense? But k is still 5. I've considered so far. Now, if I want to consider the next item, would this help? I've considered k items so far, and I have my BKW represents the maximum benefit that I can get by considering k items, and so far I have used up the weight W. I still have big W minus this W weight to fill, and still have the maximum benefit that I want to get. Can this help?
No.
Yes, it can. If my k plus 1th item has more weight than this, does that mean we should discard it?
Yes.
No, it is some of those small w's.
So how will it help?
You should be able to compare the benefits of taking it as to not versus not taking it.
Exactly. So if we take this k plus 1th item, what will be my benefit. My benefit will be B, K. So I'm explaining it in the reverse of what I have on the slides. Because, so to calculate this, for example, how would you, if I give you B, K minus 1, W, will that help? Versus B, K minus 1, and then you have W minus the WK, including. So let me rephrase this. Let me re-explain this. This actually tells that I've considered K items and I've used up W weight, right? To find this value, I have two choices. When I consider K minus 1 item, either I choose K or I don't choose K item. And that's where I reach here, right? This is after I've considered K items. So the step before this is, I have considered K minus 1 item, and then I made the decision, either I chose the Kth item or I did not choose the Kth item. So if I did not choose the Kth item, then this is equal to this, right? Because there is no additional weight. Whatever this was, it still it is. But if I did choose the Kth item, then I have to consider this, because I'm going to add the Kth item. So what benefit did I have? What was the maximum benefit that I had considering K minus 1 item when my weight was W minus WK? Because if I choose the Kth item, then I will have to add that weight. So when I make that choice, this will actually become K and W, because I'll be adding WK to it. Does that make sense? So after I've considered K minus 1 item, let's say P1, P2, PK, K minus 1, PK, and then you have Pn. So far, I know what's the maximum benefit I can get from this. And that is my B, K minus 1, W. Say some value. Right? Now, I have to make a decision whether to choose this or not. So if I make the choice, say after making the choice, whether I've chosen it or not chosen it doesn't matter, but after considering this, if say this was B, K minus 1, BK, W, then there are two situations. Either I chose it, if I chose it, then this must be BK minus 1, W minus WK. Because then this WK is going to get added to this. Or, if I did not choose it, then this is same as, so this is either equal to this, or this is same as B, K minus 1, W. See, this value I'm trying to figure out, but I'm writing the recurrence in a reverse order. So this gives me the value if I chose the Kth item, this gives me the value if I did not choose the Kth item. Let me show you this. So if you look at this, so ignore this first line first. I'm going to explain this in a bit. I got 3 minutes, so I'm going to explain this later. Look at this line. This is my benefit by not choosing the Kth item. And this is my benefit, the whole thing, by choosing the Kth item. So if I choose the Kth item, then my weight before choosing the Kth item must be W minus WK. So what is the benefit that I get by considering K minus 1 item when weight was this? Because if I choose the Kth item, this weight will be added, and then this whole thing becomes W. Right? W is my final weight after choosing the K, or after considering the Kth item. So it should be W minus WK, and then I chose the Kth item. You add plus WK, and this cancels. W is same as W. But if I choose the Kth item, I lose on the weight. but I benefit. I get to add plus BK, the benefit of choosing the kth item. Does that make sense? And so the benefit of choosing the kth item versus the benefit of not choosing the kth item, we will have to compare these two. Whichever one is the maximum, then we basically choose that. Does this make sense? A little bit? A little bit? Okay, I'll show you the table maybe then. Now, what is the first line?
Base case.
The base case, and the base case is, I am looking to, this is my exact weight W after considering key items. Now, this is my exact weight W after considering key items, and the weight of the kth item is greater than this W. Then could we have chosen the kth item? No. If the kth item is greater than the weight that I have here, then there is no way I could have chosen the kth item, and so the answer is B, K minus 1 W. But if the weight of the kth item is less than W, then we have a choice. We can consider it or we may not consider it. And then we compare the two options. If I do not choose the kth item, what's my benefit? And if I choose the kth item, what's my benefit? And I compare the two, the max of the two is what this will get. Some of you might have stopped listening to me like a few minutes ago. If that did happen, then obviously you did not understand. But the last line that I mentioned should clear it up. I am trying to figure out, let's do it one last time, and I want everybody to listen. With the open mind that you will understand it this time. I know the time is up, but give me one more minute. Forget everything else. Forget which problem you're solving. Forget the different, just look at this. What is BK minus W? BK minus W is the maximum benefit that you can get by considering K items, and the exact weight of the items chosen is W. Okay? The maximum benefit that you can get by considering K items, where the exact weight is W. Now, while considering the kth item, you may have chosen to keep it, you may have chosen to not keep it. And that's the two situations that you have here. If you chose not to keep it, that means the K minus 1 item itself was weight W. Considering K for K minus 1 item would have made the weight W because the final weight is W. Right? And you chose not to keep the kth item. So what's the benefit of doing that? Compare that to the benefit of choosing the kth item. If you chose the kth item, then the K minus 1 item, what weight should they have? That after choosing the kth item, the final weight is W. Then the K minus 1 items should have the weight W minus WK, and that's when if you choose the kth item, your weight becomes W. This plus the benefit of choosing the kth item. You compare this number, this whole thing is one number. Compare it with this number, and the maximum of the two should be given to this. Now, if the kth item itself had a weight that is greater than W, then you could not have chosen the kth item, and so the benefit is just this. That's your recurrence relation. Now, given this recurrence relation, again, it's simple. In this case, also you form a 2 by 2 table. Let me just show you. I have basically. Why is my thing not moving? Give me 1 second. So again, take a look at the slides. The slides has it's one step by step. Come on, less time. So it step by step shows you that if you have the items and if you have the weight, then you basically go to choosing the item is an option. So initially, what does B0W mean? You've considered no item. What would be the benefit? Nothing. So all are zeros, right? And then you do basically consider the next one, I 0 to n. So BI of 0 is, what does this mean? You consider how much item you want, but the total weight is 0. Obviously, you cannot take any benefit. You got no items, so you can fill zeros here. And now comes the thing. These are the items and their, the weights and their values. Now, would you consider this item? If you look here, the maximum weight allowed in this row is 1. Now, based on that, you have to make this decision. Can you choose in this slot, when the maximum weight allowed is 1, can you choose the first item? The answer is no, because the weight is 2. So you got basically 0. Now, can you choose the next item? See, the weight allowed is 1. Yes, you cannot. And so you keep doing it. Now, actually, you're doing it this way. So, can you choose the first item when the weight allowed is 2? Yes, you can. What is the benefit? 3. Then, can you choose the next item? Can you choose this one? Can you choose this one? The maximum weight allowed is 3. You can still choose it. And so you keep doing it. Basically, you will get, if the maximum weight allowed is 5, and you're only considering one item, you can choose it. So fill up this, and now you basically fill up this next one. The maximum weight allowed is 2. Can you consider the next item? No. Can you consider this item when the maximum weight allowed is 2?
No.
You cannot consider this, but you could still consider the first item. And so the benefit at this point is 2. After considering 2 items, the maximum weight allowed is 2. You can still do this. And so you keep doing it. 4. And then, so my point is that now you can consider the third item after number 3, 4, and 5. And so you fill this table. You have the number of items here and the maximum allowed weight here. And you fill this table up using the 2 reconciliation. You have the solution to the knapsack problem. The very last number that you have here will give you the solution to the knapsack 01 knapsack problem. And the same way you can reconstruct which items you have chosen by keeping the parent information. Very much like LCS. And so it can be done. Take a look at the slides. Take a look at all. I have basically in great detail I've provided each and every step. And so you should be able to figure it out. All right. Thank you guys.